First, I ask you pardon for the inconvenience caused for the last day, and I am grateful to the Professor Marcus, his willingness to give the lecture today. The conference is included in the seminar, in the subject of the seminar of the Master Technology and Communications System. The conference is also sponsored by the Spanish section of the MTT Antennas and Propagation Spanish chapter, and also thanks to the Telecommunication School and the University of the La Coruña by the facilities provided with the Professor Marcus Ruth. The conference is entitled "The Performance of the 3G and 4G Wireless System," and the Professor Marcus Rupp was born in 1963 in Welking, Germany. He received his diploma engineering degree in 1988 in the University of Saarbrücken, Germany, and his doctor engineer degree in 1993 in the Technical University of Darmstadt, Germany, where he worked in the designing of new algorithms for acoustical and electrical echo compensation. From November 1993 until July 1995, he had a postdoctoral position in the University of Santa Barbara, California, where he worked on the description of the adaptive filters with impact on neural network and active noise controlled. From October 1995 and August 21, he was member of the technical staff in the Wireless Technology Research Department of Bell Labs Laboratory in New Jersey. And he has an ample experience in the wireless communication system. He authored and co-authored more than 300 papers, including 50 patents on adaptive filtering, wireless communication, and rapid prototyping, as well as automatic design method. And after beginning, por favor, tenéis que cumplimentar las personas asistentes al seminario.
Thank you very much for the nice introduction, and thank you also for inviting me, giving me the opportunity to speak here. There's still people coming in, so there's plenty of spaces here in the front. Oh, okay. Now we should wait. Okay, let's get started. So you can see on the first slide this is work that I do not do all by myself. In fact, there's many more people involved. I just gave you here the most important names, and at the end you will see some slide how many people are really needed to do all of this. Let me first talk about what the problem is that we are facing here. We want to look into MIMO radio communication system, modern cellular wireless systems, and we want to evaluate how well they are working. The question, though, is how do you approach this? There are several ways. You could start theoretically, or what is mostly commonly done today is by pure simulation, like MATLAB simulation. People abstract, they use models, and then there's always some numbers that come out. With the numbers you form figures, and that is what you present in your papers, and you're very happy, and everybody seems to be happy about it. Of course, you may have some doubts whether this is the right numbers, and in order to look really into it, you would have to do experiments, you would have to do measurements. You can come from the very extreme end and say, okay, it only makes sense to look at the final product. This is your cell phone together working with the base station. This is what I get at the end. But that doesn't tell you extremely much about what the quality of the transmission system is. This tells you very much what the quality of the manufactured item is. Yeah? It may be done in a very well way. It may be done in a very poor way. You don't know. It's not a matter of the standard how well they implement these things. So as a matter of fact, you could do a prototype where you have more flexibility, but then if you build a prototype, usually it takes almost the same time to build the whole product. So you're not getting faster there. You only gain a little bit of flexibility. Therefore, what we decided is we are positioning ourselves here somewhere in the middle. We do test beds. And what test beds are, this is something I'm going to tell you now. By the way, you see these acronyms here, T1 to T5. You will see them on almost all slides, and they refer to papers that are coming at the end. At the end of the slides, there's a list with them. So if you're interested, then you can read more. All the slides that I'm going to present, they are available for download from the publication database in Vienna, and I will send around a link, so maybe through Luis or somebody who has your email list, we can mail it around and you can download it. And also on these references at the end, there's all links included. You just click on them and then you download automatically the paper from the publication database. So it's very convenient for you. Okay, back to the question, what are test beds? So what we have built here is an equipment that is capable of transmitting and receiving, as you can see here. It's basically a PC with some additional equipment. And what you for sure need is some baseband hardware and RF hardware, which connects to antennas. And they may be at a position of a base station, somewhere high up. You will see it on the pictures later on. Or you may emulate somehow here a receiver, a mobile communication receiver, where you have smaller antennas. And typically we have them located at the XY positioning table, because what you want to do is you want to do experiments that can be repeated somehow. If you just measure a point-to-point connection, let's say from here to here, you may get a certain result. But if somebody wants to repeat this experiment, he gets a completely different result. Why is that? Well, even if the distance is exactly the same and the equipment is exactly the same, the environment may not be the same. You have different reflections, different scattering. Yeah? So you never get the same result. But so how can you do experiments that somebody can repeat? Well, you can do that by measuring not just a single connection, but a whole ensemble of connections. And that's what we do here by this XY positioning table. We move the antennas by step engines by, let's say, lambda or quarter lambda, step by step in XY positions. And then we measure, let's say, 10,000 of them, and then we average over that. If somebody would repeat this, he would get pretty much the same result. You know? Of course, if you have a completely different environment, then you get a different result, of course. But at least it's something you can repeat, and we can repeat. We can do it in a week from now, and we get the same result, while if we just pick a certain point to point, we never get the same result. This is one of the major problems with drive tests, for example. Companies like to do drive tests. They drive around in a city with their equipment and measure how often it works. But if they would do the same test again just the next day, they get different results, because the car is never driving exactly on the same locations at the same time and not having the same environment. So it's very difficult. So what we have now is a system that transmits over 4 transmit antennas and has 4 receive antennas. Recently we upgraded this, so we can even support 12 transmit antennas now. We had a bandwidth of 5 megahertz. The measurements that I show you will be 5 megahertz. Our new system will be capable of 20 megahertz. And we have a center frequency at 2.5 gigahertz, exactly where LTE is right now. Here are a few first images. This is what we have on the roof of our institute. So about 35 meters high, there's a pole, a telescope pole, And at its end, you see this standard Catrine antennas that we are using. They're common antennas that's being used for base stations these days. And then at the other end, you see this XY positioning table where this is a slightly distorted antenna mounted here that is moving there. There's also a phi direction, so we can rotate the system also. And this is pretty much how it looks like, so you can move in X and Y direction. We support an WiMAX MIMO with 2x2 antenna systems. Unfortunately, only an older version, the 2004 version. And there's also a simulator which you can download if you want to experiment with that. Unfortunately, there was not so much interest afterwards in WiMAX anymore, so we didn't have enough power to continue with that. There's, of course, newer versions of WiMAX which are somewhat better. Then we support an MIMO HSDPA transmission. Standardized are 2x2 antennas or 2 transmit antennas, but we also have some ways of supporting 4 antennas here. Also in the dual transmit mode, that means that we have dual streams on one connection, which I will explain later. And then recently we started to move into long-term evolution, which now we are also supporting multi-user and multi-base stations, which means we can even support 3 base stations with 1 receiver and see how interference alignment, for example, works. There's a little movie that I'm going to show you.
The developed Vienna MIMO testbed primarily consists of a PC and radio frequency hardware with transmitter capabilities, channel realizations in form of a physical channel or channel emulation, and a PC and radio frequency hardware with receiver capabilities. We use XY positioning tables at the transmit and the receive side to achieve different channel realizations. An easy-to-use interface was developed to operate the overall testbed from 1 or more user PCs. Using this setup, a transmission can be performed from any PC in the local area network without the requirement for specific hardware knowledge.
So obviously the students have a lot of fun working with this. What you have seen now is about 5-6 years old. This was the first running equipment that we had. And as I mentioned, we extended this. Now this is how it looks today. What you see here is all equipment in one room. On the one hand, you see here 1, 2, 3 transmitters and 1 receiver. They are a lot smaller than what you have seen in the movie. And one of the reasons we made them smaller, we use this particular form factor here, is because this fits exactly into a car with some batteries, and you can run it for a couple of hours while driving through a city. And by this we can also do speed measurements for higher speeds. Here in the back you see the Catrine antennas that you have seen on the pole. Now they're mounted on a linear guide. The guide is about 4 meters long, and by this you can move the antennas towards each other or away from each other. You can even move them jointly, which is an interesting experiment. And also in the back you see here some fixed link connections. That is what we need for the feedback. I'm going to explain that later. So all this equipment needs to be set up somewhere, and then you can start your experiments. The test bed is based on essentially on MATLAB code that makes it very flexible. So all these equipment that you see here connects to MATLAB. You generate the standard compliant signals with MATLAB. You can also invent your own standard and develop that and send it through over the network, over the test bed. And then at the other end, we capture it, feed it back into MATLAB, and then we do back processing to decode all the material. So the actual transmission is in real time, but the decoding is not in real time. That takes a while. In order to make these measurements more efficient, you have seen here with the XY positioning table, you easily have like 10,000 of measurements. So you gain terabytes of data, and which you have to process. In order to do that efficiently, we have a pool of PCs, like 50 PCs that run in parallel, and then it still takes a couple of weeks to get all the number crunching done. Okay, here's another picture. You see the students working very eagerly on making everything working. And the rest of the talk now is about various standards. So I very quickly give you an insight in WiMAX, HSDPA, and LTE, just that you have a flavor of what is important for the measurement. I expect that you have some background of understanding that. And then the major part of the talk is about the measurement results. I have measurement results on HSDPA and WiMAX, and some simulation results from LTE, which are, of course, not the same as measurement. But yeah, there's a question.
Marcus, I'm very curious about 2 points. What kind of baseline hardware do you use? Do you develop your own PDAs or rely on some manufacturer?
There is, first of all, there is the baseband boards that map the signals into the analog world. That is bought by some companies. I can give you some links to that. But then the RF front end, the analog front end, that is self-built. We build it in such a high linear form that you can go up to 100 watt, and you still have a linear transmission. So that is very difficult to achieve otherwise.
And the other point is, perhaps it's not very, but just to get a flavor, how much does it cost to fill that room?
In terms of equipment, I would say $500,000. In terms of personnel, that all the students that need to work on this, it's another $1 million or so, because it takes, well, it took us 8 years to get there. Quite a lot. And I would say if you are interested in, first you need to get there, and then to maintain it, you need to have at least a group of 5 to 6 people that you permanently have available from different disciplines. And once you are done with the measurement campaign, you expect 20,000, 30,000 euros on equipment to replace. A lot of things are damaged afterwards. Kind of expensive. Okay, let's start. WiMAX in the brief, and feel free to interrupt me if you have a question. So what is the idea with WiMAX? Basically, you see here the transmission chain. What you have is an encoder, a Reed-Solomon encoder. It turned out it was not a very smart encoder. Unfortunately, by now they have replaced that by a turbo code, which is a lot better. At the time, that was not available. We looked then alternatively at LDPC codes, which were even better than the turbo code that came up later. But yeah, all of these things are implemented by now. In a way, it's very smart because it allows you an adaptive symbol mapping. This is shown here. So you can select 1 out of 7 possible symbol mappings. And if you have a very high quality of a channel, you can transmit more bits per second than if you would have a low quality. And there is some convolutional encoder with some puncturing scheme, which allows you to scale the bit rate. So this is basically what you can select from. You have 1 out of these 7 possibilities here with different modulation and coding. And if you count correctly, you see that with 3 bits of feedback, you can select 1 out of these. Yeah, even you have 1 bit left. This is very good for us because essentially what you have seen is a transmission scheme that does not allow for feedback. We don't have a feedback channel, which is not very problematic. If you just have 3-bit feedback, that means you have, in this case, seven possibilities. You just transmit all 7 of them, and later at the receiver you select which one you are interested in. As long as the channel is not changing very rapidly, this you can do. And in fact, for the stationary channel, we looked at how long is it more or less stationary, it's not changing, and this worked out very well. So as long as we have not too many possibilities, this is a good method. In WiMAX, it's the same as in LTE. You have an OFDM structure, and typically in the beginning you have a preamble with some training, pilot symbols. You need something for synchronization, pilots for channel estimation, control information. Then, of course, your actual data that is being transmitted. There's a lot of additional pilots and even a zero subcarrier. And you need a lot of guard bands for protecting against your neighbors because you do not want to interfere with them. So at the end, you see here, out of the 256, only 192 is being used, and the beginning is also not being used. Out of that, you can already expect that the efficiency of such a system is not extremely high, cannot be. This is one of the first experiments that we did. You see again the antennas on the roof, and you see a view through the window of the neighboring building. And inside that room, we have our XY positioning table here with 2 antennas. And we do experiments. So in this case, we have a line of sight connection directly from outdoor to indoor, but we also looked at non-line of sight, also from outdoor to outdoor, so various things. How do we do this automatic measurement? So as you can expect now, we changed the adaptive modulation encoding scheme from 1 to 7. And then there's also in WiMAX, there's an Alamuti scheme that supports 2 antennas. So we do the same on the Alamuti mode, on the SISO, single input, single output, single antenna mode. Then for 2 antennas with the Alamuti mode. And then out of curiosity, we were interested in spatial multiplexing. That means now we have the individual adaptive and modulation encoding schemes, individual for each of the 2 antennas. That makes 7 to the power of 2 equals 49 possibilities. Now for each of those, you select different transmit powers, and in this case we changed them in steps of 2 dB. And then, of course, for each of the positions. So in this case, we had the XY positioning table going through 506 positions. So at the end, you can figure out there's thousands, 10,000s of measurement points that you measure, and you have to evaluate them later on. Essentially, what came out here was that, first of all, the code that's being used, this Reed-Solomon code in WiMAX, is a really poor code, and I will show you a picture in a minute where you see that most of the losses that you would expect, they come from this code. But you can change that by using a turbo or even LDPC codes, and you get tremendously better. But also the channel estimation that is required in order to run the decoder for coherent detection costs something. And what you see here is for the different transmission schemes that we have been using, the loss in performance just because of the channel estimation. This is the best channel estimator that we could build, and this, what we call Gini-driven here, is not feeding the channel information because we don't have it. It's a measurement. Yeah? It's not a simulation, but you can deduce most of it by using all the data as training data that you transmit. So in this case, you have a tremendous amount of training data, and you would expect to get very close to the true value. So what you see here now is that if you just have a least square, a simple least square estimator, compared to the Gini-driven, you can lose up to 3.2 dB. 3 dB, that's quite a lot. So, and if you do a very clever estimator, you still have up to almost 2 dB losses here. So there's a lot that adds on losses. Here you see a simulation. This is for a simple AWGN channel, but we were interested in this Reed-Solomon decoder, and indeed it turned out that even for AWGN channel, you are very far away. This would be the channel bound here, very far away from the channel bound. As soon as we included LDPC codes, we were tremendously better. So it's about 7 dB that you gain just by the right coding, and then it's just the 2 dB here that are missing because of the channel estimation. So in this case, it is relatively simple to say where the losses come from. There's a picture here. There you see the different codes, LDPC code, turbo code, Reed-Solomon code, and this for the different channel estimators. And if you start with the best that you can have, a Gini-driven LDPC code, and say the loss is 0 relatively, then you see you can lose up to 6 dB just because of combinations of poor coders and loss in channel estimation, which is quite a lot. Okay, this was just the first experiment. Let me move on quickly to HSDPA, and then we do really the measurement campaign and the comparison. HSDPA is somewhat similar, but it's not an OFDM system. They started right away with a smart turbo encoding, and they offer a puncturing scheme with rate matching, so that's quite cleverly done. On top, they also offer a pre-coding here. That means now we have additional feedback. We do not only have the CQI, channel quality indicator values, that select your adaptive modulation encoding scheme. Now, additionally, there's also information which is called the pre-coding indicator to select this pre-coding matrix out of a fixed set. Now, you see the number of bits increases depending on the mode. There's a 5-bit feedback for CQI in the single stream mode and a 4-bit feedback for the double stream mode, plus the 2 or 4 bits for the PCI. Now we have not 3 bits, we have a lot more bits. And now it starts to be being difficult to transmit all the combinations, because by the end of the last combination, the channel would have changed. Then it's not the same channel anymore. So we decided to do something different here. And what we did different is that we had to include what we call a mini receiver solution. Mini receiver solution. What it does is it is a small part of the MATLAB code, but not the entire decoder. It's just a small part that figures out what the quality of the channel is. And this information is then fed back via the directional links that you saw on the images to the transmitter to tell him this is where you should be in your transmission. So that takes, of course, a while. That gives us a certain delay. But since we are not decoding entirely, we just want to have a quality indicator. It's relatively fast. Okay, I don't have that picture, but that's okay. What is this quality indicator? It's essentially what we call the post-equalization SINR, so a signal to interference and noise ratio. And you have your signal power, you have your noise, you have your inter-symbol interference, and you have interference from, in this case, from your scrambling and spreading codes. In HSDPA, they are orthogonal, but once they are sent through a channel, they are no longer orthogonal. So they interfere with each other, and this causes also interference power. Now, you have to estimate that, and you plug in your potential solution for a good equalizer with a channel estimator. Then you see how good it is. That is what you expect, what the receiver would receive, and this information you send back. The first thing that we did was a simulation, and in simulation everything looks very nice. You see, first, don't look at the black curves, I'm coming to that, just look at the colorful curves here. So we start with a 1x1, a single antenna scheme, and then move on to 2 antennas up to a 2x2 scheme. And what you see here is what we give in as a signal to interference noise ratio, and what we believe comes out as a post-equalization SINR. And we have two results here. One is a dotted curve and one is the continuous curve. Here you see it, usually the curves are lying on top of each other. And one is the correct one and the other is then what we estimate. So obviously we are doing it right. What is the strange thing with the black curve here? The black curve is for the dual stream mode, and that only makes sense if you have a very high SNR, because then you can transmit on over the same frequency band a second stream that is independent of the first one. And therefore it only makes sense if you look here at the end and there for high SNR, yes, the curves are fitting. For this area here, you would not transmit a dual stream mode, so it doesn't matter actually where the curves are. Okay, the same picture is this picture here, and correspondingly on the top you have the corresponding throughput that you would expect, because this was just the SINR, and this is the corresponding throughput for the 5 different modes. And first of all, this looks quite sound. So for a single stream mode, you can have a maximum here at about 12 megabit per second. And for the double stream mode, of course, it would double to 23 or something megabit per second. So it looks nice. Then we did measurements, and the measurements are here on the right-hand side. And you see, for the low SNR in this area here, it seems to agree very well, although we did not even fit the channels. We just took the standard pedestrian B channels and expected this to be the right situation for our measurements. But for the high SNR, it looks completely different. We were far off. Here you see our curves are bending away from the dotted lines. And also here in the dual stream mode, we hardly got any improvement. It was very poor. So for a couple of weeks, we were sitting there and debating what we are doing wrong in the measurements. And at the end, we figured out we didn't do anything wrong. The measurement is always telling you the truth. You just need to understand it right. And the error was in the simulation, because in the simulation, you don't add the synchronization channel. Why would you? Everything is perfectly synchronous. You don't make any synchronization error. But the synchronous channels in HSTPA, they are not orthogonal to the codes that you are using. So they are really a big interference, and this interference is showing at the high SNR. It's not going away. And this is the reason that for high SNR, the curves need to bend. So once we included the sync channels in the simulation we had the same picture. And then we were wondering, how can they make it that you have such high data rates for the under HSTPA in the dual stream mode? Well, the only way is you have to include a very smart receiver that does interference cancellation. It needs to take away all the interference by the synchronization channel by reproducing that internally and then subtracting it off. And this is what we did then in the next measurements. And then you see now it works. For the dual stream mode, you actually get very high data rates. But the consequence is the standard is very nice, but you need a very complex receiver in order to get these high data rates. Just having high SNR is not good enough. This is something we were quite surprised about. Okay, let me quickly tell a little bit about LTE, and then we come to the comparisons. So similar to WiMAX, this is also an OFDM system. You have a lot more freedom now on frequency and time. You see the carrier spacing is 15 kilohertz, and usually you combine 12 of them in one so-called resource block. So a receiver will have at least 12 subcarriers or multiples of 12. You have more flexibility than before. Again, you have a channel quality indicator. Now it's 4 bits, or there's another mode with 5. You have similar to before.